Hello everyone. Today we will see the ionization constant of weak acids. Okay, in the last session we have seen the ionization constant of water and its ionic product and also the pH scale. Okay, so now we will deal with the ionization constant of weak acids. Okay, now if you consider a weak acid, for example, a weak acid HX. Okay, so if you consider a weak acid in aqueous solution, correct, in aqueous solution means what? You can say HX aqua plus water also you can write, isn't it, in the liquid state, which is in equilibrium with H3O positive plus X minus, isn't it? So if you consider a weak acid which is ionized in an aqueous solution, the equilibrium can be represented as this. Okay, this is also aqua. Okay, now what happens is, you have to write the initial concentration. Okay, initial concentration which is in molar. If you say that if C is the initial concentration of this weak acid means what? Acetic acid. Okay, say example acetic acid. If C is the concentration of acetic acid, then the product is 0 because product is yet to be formed. There is only reactant in the initial state at the time T is equal to 0. Okay, you know this. Now, if alpha be the extent of ionization. What is extent of ionization? Extent of ionization means, for example, if you are remembering, we said that in a strong acid, for example, HCl, we said that there is 100% ionization, isn't it? Here, it is only, when we talk about acetic acid, we have said that it is only 5% ionization. So, only 5% is the extent of ionization of acetic acid. So, that is meant by X. So, we represent as alpha. Clear? So, if alpha is the extent of ionization, then you can write the change in this concentration. Okay, or the change is, you can say minus C alpha. Why you wrote minus C alpha? Because minus sign indicates that the reactance goes on decreasing. And alpha is the extent of ionization and C is the concentration, initial concentration of the weak acid. Now, if alpha is the change, that is minus, it is decreasing, that much is increasing in what? That much is increasing in the product side, isn't it? If C alpha is decreasing, then the change will be plus C alpha and plus C alpha, isn't it? So, how much here it is decreased, that much product it is getting increased. Correct. Now, we can say at equilibrium concentration in molar, you can say what will be the equilibrium concentration? Initially it is C, and what is the change? C alpha. So, at equilibrium concentration it is C minus C alpha, and here it will be simply C alpha plus C alpha, and here also plus C alpha. Correct. So, what is C? C is the initial concentration. What is alpha? Alpha be the extent of ionization. Correct. At a time T, when it is beginning, only reactant is there. Product is 0. And if alpha is the extent of ionization, C alpha is the change in concentration, isn't it? So, how much is decreased in the reactant, that much is increased in the product side. Clear? Okay. Now, at equilibrium concentration, we will get initial minus the change will give you at the equilibrium, that is C minus C alpha. Here it is C alpha and C alpha. Now, as we discussed earlier, if you write the equilibrium concentration as Ka, okay, Ka, that is equal to concentration of the product, that is C alpha into C alpha divided by C minus C alpha. Or you can write what? You can write C square alpha square divided by, if I take C outside the bracket, then I will get 1 minus alpha. Correct? Isn't it? Is it clear? Okay, now I can remove 1C. So, it will be C alpha square into 1 minus alpha. See, This is the equilibrium concentration. This is the dissociation constant or ionization constant of a weak acid. Or simply by this equation, see, by the first equation, I can write the equilibrium constant simply as Ka is equal to concentration of H plus, or you can write H3O plus into concentration of X minus divided by the concentration of undissociated acid. So, we can say at a given temperature, we know it's a temperature dependent, correct? Like equilibrium constant, dissociation constant is also a temperature dependent factor. So, at a given temperature, what does this Ka indicates? Ka indicates the strength of an acid Hx. Now, the value of Ka decides whether an acid is strong or acid is weak. You got it? So, depending on the value of this Ka, you can say whether the given acid is strong or given acid is weak. Now, a generalization we can say, larger the value of Ka, remember, larger the value of Ka, stronger is the acid. That is generalization. So, if the stronger is the acid. So, if the value of Ka is larger, you can say the acid is stronger. So, you know the stronger acids like HCl, HNO3, the Ka will be larger. But what about the pKa? It is inverse, right? So, smaller the pKa, stronger is the acid. But larger the Ka, stronger is the acid, because Ka and pKa are inversely proportional. Now, if you want to have some values, the magnitudes or values of the ionization constant of some selected weak acids, you can go through it in the textbook. It is given. Hydrofluoric acid, it is, for example, say HF, it is having 3.5 into 10 raised to minus 4. Whereas phenol, there is organic one, or acetic acid, it is 1.74 into 10 raised to minus 5. That is acetic acid. So, see the difference? So, from the value of Ka, we can calculate how much strong or how much weak is the acid. But pKa means the inverse of this. If pKa is decreased, stronger is the acid, isn't it? Stronger is the acid. Or you can say pKa is equal to minus logarithm of Ka. Am I right? Minus logarithm of Ka. Why? We know pH is equal to minus logarithm of H plus. Correct. Now pOH is equal to minus logarithm of OH minus ion. Correct. If that is the case, you can say pKa is equal to minus logarithm of Ka. So, is it clear? Okay. Now, if you want to calculate the pH, of a weak acid, there are some steps to be followed. Okay, you have studied in this the way or this type of calculations you have done, but the important thing is in such a case, if you want to calculate the pH or the hydrogen ion concentration of a weak acid, then you have to know that how many reactions are possible in such a type of reactions, or which I mean how many type of proton transfer reactions are possible. Then only you can say it is an acid, right? So how many types of proton transfer reactions are possible, and from that reactions, whatever is the value of Ka is greater, that you should take as a primary reaction. So that is the funda. So, how many reactions are there? So, in the examination point of view, they will give you the Ka. Okay, they will give you the Ka of all the reactions which is happening there, and from that Ka, you have to take the value of Ka which is largest, or you can take it as a primary reaction. Okay, the rest all is same as what we have done earlier. So, first is balance the chemical. First is you have to write the equation. Then you have to balance the equation. Then you have to find which is of the greater Ka. Then in the tabular, then we have seen what is the initial concentration, what is the change, what is the equilibrium concentration, etc., etc. Okay. Now we will see it through a example or a numerical. Okay. So that is, see, in this numerical, it is said that the ionization constant of HF is a weak acid, right? So the ionization constant of HF is given, that is Ka is given. Now calculate the degree of dissociation of HF. So what you have to calculate? You have to calculate the degree of dissociation, that is alpha. Clear? And also in its 0.02 molar concentration is given. So calculate the concentration of all species. All species means concentration of H3O positive, okay, concentration of H3O positive, concentration of F minus, and also the concentration of HF in the solution. And after that, you have to calculate the pH also. So in one numerical, you can have all these things. Okay. Now, please listen carefully. In these type of problems, what I said is, in the case of a weak acid, because weak acid means what? Strong acid means full dissociation happens. For example, HCl, H plus and Cl minus is only there. So there we don't take the dissociation constant values. But in this case, we have to take the dissociation values. But so in solution, if you say, for example, if you know HF, or we have said acetic acid in the last session. So here if I take HF plus H2O, H2O is also there, right? So you have to take this equation and then balance it. Now see, instead of HF also there is one more reaction here. That is, first you have to write the proton transfer reactions. How many proton transfer reactions are possible? That means the acidity level you have to know. One is, you know, the HF ionization is taking place in aqueous solution. So it will be H plus and F minus. The Ka is given. Now the second is H2O. The H2O can take an acid and base to give proton, that is H3O positive and OH minus ion. There you know the Kw is 1.0 in 10 raised to minus 19. Then what you have to see, which Ka or Kw. Kw is for water and Ka is for the acid. Now which of these has got a greater K value? Definitely the Ka is greater than the Kw. So which is the principal reaction? The principal reaction here is the first reaction. So that you have to decide first. So while going into a problem or a numerical, you have to know which one is the principal reaction, or you have to find out by looking at the K values which is the principal reaction. Is it clear? Okay. Now once you have assigned the principal reaction, then you have to write once again that reaction, and then we will do it. See, I have done, since the Ka is greater for this, I have written it as Ka is greater, more greater than Kw. So our principal reaction is which one? HF plus H2O giving H3O positive plus F minus. Now what you have said, the initial concentration, the concentration is given how much? The concentration of HF is 3.2 into 10, the degree of dissociation is 0.02. Okay, so the initial concentration is what? The initial concentration is 0.02. So the initial concentration we can say it is 0.02. Correct? So that is when time t is equal to 0. That is, the reaction is going to start. There is no product here. This you take as constant, you know, water is always taken as constant. So here you will get 0 and 0. Now what is this change if alpha? If you suppose alpha is the extent of dissociation, you know, degree of dissociation, because we have to find alpha, that is degree of dissociation. So we have to find that. So we are writing that. So if alpha is the degree of dissociation, then the change is minus 0.2 alpha, correct? Minus 0.2 alpha. This is plus 0.2 alpha and this is plus 0.2 alpha. Is it clear? Okay. Now at equilibrium concentration, what we have derived in the last session, in the last thing, then 0.02 minus 0.02 alpha is the change or the equilibrium concentration in molarity. Okay, equilibrium concentration in molarity, 0.02 minus 0.02 alpha. Now here it is 0.02 I'm really sorry, it is 0.02. Okay, so it is 0.02 alpha, and here also it is 0.02 alpha. So is it clear? Okay. Now now you have what you have to do. You have to substitute the values in the equilibrium reaction concentration. That is Ka is equal to product concentration by reactant. So 0.02 square alpha square divided by 0.02. If I take out, then 1 minus alpha. Clear? So 0.1, 0.02 and 1.02 cancel. So you will get 0.02 alpha square divided by 1 minus alpha is equal to Ka. Ka is given 3.2 into 10 raised to minus 4. Here you have to calculate the alpha. So please calculate the alpha as a homework. Okay, please put. So you will get a quadratic equation, and from the quadratic equation, just you cross multiply this, that is 3.2 in 10 raised to minus 4 into 1 minus alpha. So what you will get? 3.2 in 10 raised to minus 4 minus 3.2 in 10 raised to minus 4 alpha. That is equal to alpha square. So you can write what? 0.02 alpha square minus this is minus, no? Yes. So alpha square, if you divide it into 0.02, you will get alpha square plus 1.6 into 10 raised to minus 2 alpha minus 1.6 into 10 raised to minus 2 is equal to 0. So you just, what you have to do, you have to simplify this equation and you have to find the alpha. That's it. And I have given a hint as that this is a, just take the form in a quadratic equation and get the alpha as minus b plus or minus root of b square minus 4ac by 2a. That we have done earlier. So no problem. So if we get alpha, for example, say alpha is equal to say 0.12. Okay, if alpha is equal to 0.12, then what is the question they are asking? The question asking is calculate the concentration of H3O positive, the concentration of F minus and the concentration of HF. Now coming back again, what is the concentration of HF? That is 0.02 into 1 minus alpha, isn't it? Or isn't it? That is C into 1 minus alpha. Correct. So one by one we can do it. That is, first we will see the concentration of H3O positive. H3O positive is 0.02 into alpha. That is 0.02 into what is alpha? If it is 1, 2, it is this thing. Correct. So likewise you can calculate everything. And for example, if you want HF is 0.02 into 1 minus alpha, that is 0.1 minus 0.12. So you just calculate and get the answer. So this is how you can get, and if you get the concentration of H plus, how you will calculate pH? How you will calculate pH? pH is equal to minus logarithm of H plus ion concentration, isn't it? So if you get H plus, you can very well calculate the pH. So clear? Okay, so just do it as a homework, the calculation. Okay, so this is how you are doing the numerical for a weak acid. So is it clear? Okay. Now in the same way, we can say, or we can calculate, or we can detect the ionization constant of weak bases. Earlier we have done the ionization constant of weak acid. Now we will see the ionization constant of a weak base. Okay, so Kb, that is for weak base. Okay, for weak acid it is Ka, and for weak base it is Kb. For example, in this case also we will have a weak base, that is weak base means NH4OH. Simply I am saying. So MOH. Okay, generally I can write MOH aqueous will give you M plus OH minus. Correct? M plus OH minus. Both are in aqueous. Now you can write the same way as Ka. Kb is equal to the concentration of M plus into concentration of OH minus divided by the concentration of MOH. Correct? In the same way you have derived. So it's a homework. That is a derivation. Homework. The derivation you have to do as the homework. Correct? In the same way we will get Kb is equal to C alpha square by C into 1 minus alpha. See, this you have to derive it in the same way as what we have done in an acid. We have done in an acid as Ka is equal to C alpha square into 1 minus alpha, isn't it? By how? This. You have to write like this. This is a base plus water giving like this. Then initial concentration, change, equilibrium. Then you have to put these values in the equilibrium constant. But the problem is here we have written Ka. The other one you have to written as Kb, and you will get C alpha square by 1 minus alpha. So this you have to get it through homework. Clear? Okay. Now we will see what is the relation between Ka and Kb. Now you know what is Ka and what is Kb. Correct? Now you will find a relation between Ka and Kb. What is the relation between Ka and Kb? Okay. Now if you consider an example, both an acid and a base. See, for example, in the first case, we are having ammonium ion plus water. Okay, I am not writing always aqua because it is necessary. So, ammonium ion and water, this will liberate proton. Okay, this will liberate proton, this will accept proton. So, this is an acid. Okay, and this is a base. So, you will get H3O positive plus H3O positive plus NH3. Correct? And if you write the Ka is equal to, concentration of H3O positive into concentration of ammonia divided by the concentration of NH4 plus. Am I right? Okay, because water is taken as a constant. Now you will be given as Ka is equal to 5.6 into 10 raised to minus 10. Say, this is the value. Okay. Now, in the next reaction, in the basic reaction Kb, NH3 plus H2O, correct, gives what? NH4 plus OH minus. So, here it will act as a base, and here this act as an acid, correct, this act as an acid and this as a base, correct. So, acid means it will give out proton and form the OH minus. So, this will be the conjugate base for the water, and this will be the conjugate acid for the ammonia. Okay, you know that, all that. Now, the Kb is what? The same as NH4 plus into OH minus divided by NH3, correct? And the Kb is found to be 1.8 into 10 raised to minus 5. Okay. Now, these two reactions, see, one is for ammonium and second is for ammonia. From these two reactions, what is the net reaction? If you cancel out this RHS and LHS, what will be the next reaction? Here it is NH4 plus, here it is NH4 plus, it can be cancelled, correct? Now, here it is OH minus, correct? Here it is OH minus is there. Then NH4 plus and NH4 is cancelled. Ammonia and ammonia is cancelled. So what is the net reaction? You can have 2H2O, that is H2O and H2O. What is it? 2H2O will give you H3O positive because NH3 is cancelled. H3O positive and OH minus. See? And you know what is the Kw value? Kw is 1 into 10 raised to minus 14 molar. See? If you take these three separate reaction, we will say or we can find what is the relation between Kp and Kc. Ka represents what? Ka represents the strength of NH4 positive as an acid. Correct. Ka represents the strength of acid. What is the acid here? Ammonia. And what represents Kb? Kb represents the strength of base. Who is the base? Ammonia is the base. Correct. Now, if you have the Ka into Kb, see, Ka into Kb, you will get what? You will get on calculation. If I say, see, Ka is what? Ka is, we will write this H3O positive plus NH3 by NH4 plus. So, I will write it. Okay. So, H3O positive into NH3 divided by NH4 plus, correct? NH4 plus. Now, divided by means upside down. It will be NH4 plus into OH minus divided by NH3. See, this is Ka into Kb. Clear? Now, if you knock out the things NH3, NH3, NH4, NH4, you will get Ka into Kb is equal to concentration of H3O into concentration of OH minus. So, what is it exactly? It will be Kw. Am I right? So, Kw is equal to concentration of H3O into concentration of O minus. So, from this relationship we can say Ka into Kb is equal to concentration of A into concentration of B. Clear? In the same way we can write what? In the same way in the base also you can write. If it is a basic solution, we can write what? Ka into Kb is equal to Kw. Correct? Or we can say pKa plus pKb is equal to pKw. See, the pH value, like pH value, pKa plus pKb is equal to pKw. And that comes to be equal to 14. So remember this thing, that is pKa plus pKb is equal to pKw, which is equal to 14. Okay, you can simplify it. Okay, so hope you have understood this. Correct? If you take base also, now if you are taking acid and base, now if you the expression we can discuss in the base dissociation equilibrium also. Like if you want an example, I can write, for example, that is base means B plus H2O giving BH plus and OH minus. Take this case. And then you will get the Kb. Okay, you find Kb, and then what you have to do? You have to make it as Ka into Kb is equal to Kw. So please see this, whether you can find it or not. Just what you have to do is, first you find Kb, right? Kb is BH, concentration of BH plus into concentration of OH minus by concentration of B, because water you didn't take. Now, you know concentration of water remains constant. Okay, then what you have to do? But you have to get this equation. So, for getting this equation, you have to multiply and divide this above expression. See, I will tell you. If you are not getting it, I will tell you the base dissociation also. See, B plus H2O will give you BH plus OH minus. This is the base dissociation. Okay, this is the base B. Now, what is Kb? Kb is equal to concentration of BH plus into concentration of OH minus divided by concentration of B. You got it? Correct? Okay. Now, we want this equation, that is Ka into Kb is equal to Kw. But in this way, you can't get this. Now, what you have to do? You have to multiply and divide, because the value doesn't change. So, you have to multiply and divide both with H plus ion concentration. So, what you will get? You will get BH plus into OH minus, correct? BH plus into OH minus by B, correct? That is BH plus into OH minus divided by H plus B, correct? Now you have to multiply, that is H plus ion concentration, both multiply and divide. Numerator and denominator you multiply with this, correct? You multiply this equation both with, so what you will get? Here you will get H plus, and here you will get B and H plus. See? Correct? You got it. Now what you have to do? What is Kw? Kw is H plus plus OH minus. Correct? So you can write Kw. Correct? So this is Kw. That is OH and H plus is Kw. See? Just listen. This is Kw. OH, Kw is what? Kw equals, you know, concentration of H3O positive into concentration of OH minus is Kw. So instead of this, you can put Kw. Correct? Now what is this? BH plus B into H, that is Ka. Correct? Ka. So you got Kb is equal to Kw by Ka, or Kb into Ka is equal to Kw. See? So this is how the base dissociation thing works or happens. Got it? Okay. So hope this is clear for you. Okay. Now we will see a topic, a simple topic, which is regarding the dibasic and polybasic acid. Okay, so this is regarding the dibasic and polybasic acid. Okay, now what do you mean by this dibasic acid or dibasic base or polybasic acid or polybasic base? You know, for example, if you say sulfuric acid is a dibasic acid. Now what do you mean by this dibasic acid? Which means that it has got two protons. It can donate two protons. Okay, so you know which donates proton is called as an acid. So it contains two protons to donate, so it is called as a dibasic acid. If it contains more than two, it is called as polybasic acid. For example, H3PO4, it contains 3 H plus ions. So it is it can also called as tribasic acid. Normally we say more than 2 hydrogen atoms to donate, we say it is a polybasic acid. Correct. So that then in the same way, dibasic base means if it contains 2 OH minus ion, or if it can donate 2 OH minus ion, it is known as dibasic, and if more than 2 OH minus, you call it as polybasic acid. So clear? Now we will take an example. We will take sulfuric acid as an example. For example, H2SO4. Correct. H2SO4, in the first case, what it happens? It will form H plus and HSO4 minus. Correct. And in the second case, HSO4 minus will form H plus and SO4 2 minus. See. So in the first case, it forms H plus and HX or HSO4 minus. And in the second case, this HSO4 again dissociate to form the H plus and SO4 2 minus. Okay. Now, if you say the equilibrium, for example, if I say this is the first equation and this is the second equation. If I say in the first step, I can say Ka1 is equal to concentration of H plus into concentration of HSO4 minus divided by concentration of H2SO4. Clear? Okay. And Ka2, that is the second step, you can write H plus into concentration of SO4 2 minus divided by concentration of HO4 minus. Correct. So Ka1 is called as the first ionization constant and Ka2 is called as the second ionization constant for the dibasic acid. This is sulfuric acid. Now for example, if you say like this H3PO4, it will have Ka1, then Ka2 and also Ka3 because it is a tribasic acid, and go on. Correct. And we can see that this Ka2 and A3 are smaller than this Ka1. What is it? Ka2 and Ka3 will be smaller than this Ka1, which means that Ka1 will be bigger than Ka2 and Ka3. What is the logic or what is the reason behind it? The reason is it is more difficult. It is more difficult to remove a positively charged proton from a negative ion due to this electrostatic force of attraction. See, that means, see, in this case, H plus and HSO4 minus. So this is a neutral molecule. Correct. This is a neutral molecule. Okay. This is a neutral molecule. Now, first case you have Ka1. Now in the second case, how this H plus is removed? From a charged particle. See, from a negative charged particle, a positive charge is given out. Okay, so that is Ka2. So in removing a proton from an uncharged, this is neutral, this thing, that is more than, as compared from a negatively charged ion. Correct. Or we can say that it is very difficult to remove a proton from a negative ion or a negative ion than a neutral molecule. Clear? Okay. So that is why so you can say if you say H2SO4 is a strong acid, the primary reaction is, what is the primary reaction? If H2SO4 is a strong acid, the primary reaction involves the dissociation of H plus and HSO4 minus. Clear? So this is called as dibasic and polybasic acid. Clear? So if it takes place in 2 steps, you get 2 dissociation constant Ka1 and Ka2. And in the second step, the removal of a proton is very difficult when compared to the first step. Why? Why? Because that in the second step, the H plus is removed from a negative ion. In the first step, the H plus is removed from a neutral molecule. Clear? So it is seen that higher order ionization constant, that is Ka2, Ka3, are smaller than the lower order ionization constant of a polyprotic acid. Okay, if more than 3 Ka are there, you can write like that. And the reason is, it is more difficult to remove a positively charged proton from a negative charge ion because it is having a electrostatic force of attraction. Correct? Clear? Okay. Then, now we will see the factors affecting acid strength. What is it? Factors affecting acid strength. Factors affecting acid strength. We know the most common factor regarding the acid strength is the ease with which a molecule can donate a proton. The easier the molecule donate a proton, we call that as the acid strength is very high. Or in simple case, you can say if Ka is higher, acid strength is also higher. So greater the value of Ka, greater is the acid strength. But now the question is, if I say HCl or acetic acid, you will say HCl is more acidic than acetic acid. Now what is the reason behind, or why you say that HCl is more acidic than acetic acid? So you can say, or broadly we can say that the extent of the dissociation of acid, the acid strength means what? The acid strength can be seen as the extent of dissociation, correct? How much fast it can dissociate the H plus ion or HCl into, for example, HCl into H plus and Cl minus. How much fast it can, or it is 100% dissociation, then you can say it is strong. Or if it is only 5% dissociation, you can say it is weak. So it is the extent of dissociation that depends on the acid strength is mainly depend on 2 criteria. One is, as you know, the extent of dissociation is mainly due to the strength of the acid, and second is the polarity of the HA bond. HA bond means H you represent it as a proton and A is the, for example, HCl or CH3COOH, that is H represents that. Okay, so the extent of dissociation is mainly depend upon 2 factors, that is strength of the acid as well as the polarity of the bond. So when we talk about the strength of the acid, if you have an acid like HA or for example HCl, okay, now when the energy required to break this bond, see HCl is there, if the energy required to break this bond is when it is decreased, you can say the H plus ion is liberated and it is a strong acid, correct? It is a strong acid, that means dissociation happens. So we can say when the strength of the HA bond is decreases, the bond strength decreases, correct? The bond strength decreases, what happens? The extent of dissociation increases. Clear? That is the energy required to break that bond decreases. Clear? Because if the bond strength is decreased, if HA is a very weak this thing, you can have easily break this bond. Or if the energy required to break this bond is very less, then this HA becomes a strong acid. Correct? Okay. And if this HA bond becomes more polar, see the second is if the HA bond is more polar. What do you mean by more polar? There is a difference between the electronegativity, that is polarity. That means the electronegativity between these 2 atoms is high or increased. Then you can say, or there is a marked separation. For example, HCl, it is delta minus and delta plus. If the electronegativity between these 2 atoms are increases, then you can break the bond. That means the cleavage of the bond becomes easier. Therefore, the strength of the or acidity increases. The acid strength increases. Clear? So, the acid strength mainly depends upon the bond between this acid the strength of the bond, okay, the strength of the bond as well as the polarity. Now, if you say strength of the bond, which means what? If the strength of the bond is decreased, then the energy required to break that bond is decreased, thereby the acidic strength increases, or you can say it is a very strong acid. Now, if you talk about polarity, polarity means there is a charge difference in the molecule. Now, if you talk about the polarity, we can say that this HA bond is more polar when the electronegativity difference between these two atoms, if I say H and Cl, will be very high, then the charge separation is easier, because if it is very high, this plus will go this side and minus will go this side. So we can easily break this bond. Therefore, the acidic strength increases and you can say HCl is a strong acid. Okay. But now the point is, this is a funda. But now the point is, if you talk about in a periodic table, if you talk about a group, see, in a group wise, if you talk about the acidic strength, for example, HF, okay, HCl, fluorine, chlorine, bromine, iodine. So, if I take fluorine, chlorine, bromine, iodine, the acids, hydrofluoric, hydrochloric, hydrobromic and hydroiodic acid, what is the acidic strength? It will decrease or it will increase? That is a question. That is a question. Now, if you say in a group in a periodic table, will the acidic strength increases or decreases? See, in this case or in a group, the main thing to consider is the bond strength. The bond strength. So, if it is in the same group, the bond strength is an important factor. Now, coming to the bond strength, how you will determine? The bond strength is an important factor in determining the acidity rather than the polar nature. Two things are there, strength and polarity. But in group wise, if you compare the acidic strength in group wise, the bond strength will have a more weightage than the polarity. Now you know, as the size, from the group, size increases from top to bottom. As the size increases, what happens? As the size increases, the HA bond strength decreases. Then what happens? The acidic strength increases. Simple. Correct. So this is the case when these acids are in a group wise. But when it is in a period wise, what happens? The polarity becomes more weightage than the bond strength. That is the difference. If you talk about group wise, which will have a more weightage, we will take only the consideration of bond strength, and from top to bottom as the size increases, the bond length decreases, thereby the HI is more acidic than HF. But in period wise, the polarity will make a difference, or polarity will have a weightage than the bond strength. The electronegativity increases from left to right in a periodic table. Correct. Left to right in a periodic table. So, the electronegativity also increases from left to right in a periodic table. So, if you consider, for example, I will write it here. If you consider compounds like CH4, NH3, H2O and HF. So, period means carbon, nitrogen, oxygen and fluorine. So, in this case, what happens? In this case, the acid strength increases. That is, HF is more acidic than methane. Why? Because here the polarity is increased in HF, or the electronegativity is increased in HF. So, these are the two factors which affects the acidic strength. Correct. Hope you have understood it. Okay. So, I hope the other portions like the hydrolysis of salt and buffer solutions are deleted from this textbook, the solubility etc. deleted. So, the chapter ends here. So, the equilibria ends here by this factors affecting the acid and acid strength. That is, according to the strength of the acid, strength of the bond as well as the polarity. So, here comes the end of this chapter equilibria. Then we will move on to the next chapter, that is in the next textbook. We will see the redox reaction. Okay. So, please read the textbook. If any doubt, just call me. Till then, thank you.